So yes, of course, I want to start thanking the organizers for the invitation. It's actually the first conference of praxis series that I attend to, and yeah, it's been very, very nice. I changed the title, so initially the title was about quantum thermodynamics, and of course, maybe it was not the most fitting topic for the conference, so I changed the title to super adiabatic control of complex systems, and I will essentially define what I mean by super adiabatic. So essentially, it's going to be fast control, which of course is going to be non-adiabatic. So this is going to be essentially the outline of the talk. So I will start introducing the notion of shortcuts to adiabaticity. I hope you can see the pointer. It's a bit dim. Maybe just wait a bit. Yeah. Right. So as I mentioned, the talk is going to be about fast, non-adiabatic control of quantum systems, in particular using this set of tools known as shortcuts to adiabaticity. So I will introduce them with a very general point of view, and then illustrate a demonstration of how these techniques can be used to tailor the dynamics of relatively complex systems, including quantum fluids. So that will be a second part of the talk. And in the last part, I will move to systems which I consider to be more complex because they have phase transition, quantum critical systems, and then typically it's very difficult to tailor the dynamics in these cases. So maybe I guess one first question, of course, comes, like we all know that the slow driving provides good control of the dynamics of arbitrary systems. So this is thanks to the adiabatic theorem, and you may actually wonder whether there is any need to go faster. And I guess to this audience in particular, there is no point in motivating why, for many applications, we need to speed up processes. In the presence of the coherence, sources of noise, we may want to go actually to drive a quantum mechanical system faster while still controlling the dynamics. So this motivates the introduction of this set of tools known as shortcuts to adiabaticity. And the definition is very broad. It's just any fast, non-adiabatic process that reproduces the same final state that you could achieve under slow driving under adiabatic dynamics. Yes? So you just drive a system quickly. Typically, you pump lots of energy excitations, but somehow at the end of the process, you manage to cancel all these excitations. And you are back to the essentially a steady equilibrium state with no residual friction. So these ideas have now implemented in a variety of experiments, starting here in France at Nice with cold atoms, but later on there were experiments in ion traps exploring both transport and expansions of ion chains. There's ongoing work on how to split ion chains and how to merge them using these tools. And also, they have been exploring spin systems, MB centers, and so on. Yeah? So the systems where they have been discussed, I guess they can be classified as well from a complexity point of view. So there were early ideas on how to use them for essentially single particle harmonic oscillators, but then they were also explored for transporting small ion chains, loading cold atoms in optical lattices. And I guess the focus of this talk is going to be more on this part where either we tailor quantum fluids, so many particle systems, or we explore how to drive a system through a phase transition and suppress defects also in the context of quantum annealing. This has been found useful. So if you want to follow a bit the action on these kind of shortcuts, there's this special focus issue in NJP that I'm editing together with Ki-Wan Kim. So Ki-Wan Kim is an experimentalist at Tsinghua University who demonstrated some of these shortcuts in an ion trap. And there are actually some very interesting works already reported there. So just so that you feel at home, I'm going to introduce a technique which is very simple and intuitive. It's almost just kind of 101 quantum mechanics, but this will be a universal recipe to design shortcuts to adiabaticity. So the idea is take your favorite system and just say that it is described by a Hamiltonian H0. So we assume the system is decoupled from any environment, so we have unitary dynamics. And think that there is a parameter of the system that you want to drive as a function of time. Yeah? And the idea is, at least for the construction, you are expected to be able to diagonalize the system and have access to the eigenstates and eigenvalues. Then we do know that if you drive the system slowly, the dynamics is actually very simple. It's described by the adiabatic approximation, and the time-dependent state just follows the instantaneous eigenstate of your system Hamiltonian as you drive it, and it picks up a phase, which is the dynamical phase and the geometric phase. Yes? Now, this, of course, only happens if you drive the system slowly, but the question is, could you have also this trajectory, this evolution, in a kind of fast motion video where you run it faster, but it's still the same trajectory? So, say differently, can we find a different Hamiltonianates such that the adiabatic approximation to your system of interest that can be an exact solution even when you drive it quickly, even when you drive it fast? Yeah? So how to proceed is actually, so the answer is yes, and you pretty much just, write down what you wish for. And the first thing maybe is just to identify what will be the unitary, the time evolution operator, which does the job. Of course, it's a unitary which maps any initial eigenstate of your system H0 to the desirable trajectory, a time-dependent state at time t, so in this case, the adiabatic approximation. Well, and if you know the time evolution operator, then you can just find which is the Hamiltonian which generates that evolution. So you take the derivative of the unitary and takes a product with its adjoint, and that will give you the Hamiltonian. So this is a construction which I think was also alluded to in the talk by Sophie Economou a few days back. And essentially, when you go through this procedure, then what you find is that you can always find the Hamiltonian, for which there is an exact solution as the adiabatic trajectory to your system, and you can split it in two parts. One is your initial system of interest, and then there is a second term, which is just a control field, or counter diabatic control field, which is the one which suppresses excitations away from this adiabatic trajectory. So this is the term which enforces the adiabatic evolution as an exact solution of the Schrödinger equation. You may know that this Hamiltonian was derived maybe already in 1950 by Cato, so it appeared in proofs of the adiabatic theorem, but maybe no one thought of it as a control term that you could actually realize in the laboratory. So this step was given by Stuart Rice over here with his postdoc. It's impossible to find a picture of him, so Mustafa Demir-Plak. And in 2003, Stuart Rice is one of the pioneers of quantum control in chemistry, and they had a clear motivation that maybe this was a way of tailoring the dynamics of quantum systems. A few years later, Michael Berry, the famous Berry of the Berry phase, rediscovered this pretty much with the derivation that I have introduced. And so, essentially, both works have this result that the exact term that enforces adiabatic following is the slowly driving system, or your system of interest plus these controls. Now, if the spectrum of the Hamiltonian is non-degenerate, it is always possible to write down this auxiliary control term in this form. This is not an approximation, but it really looks like first-order perturbation theory. Yeah? So you have the rate of change of your system Hamiltonian over the gaps of any of the eigenstates of that system Hamiltonian. You also see here that this term couples any eigenstate with any other eigenstate, so you may suspect that this is maybe a bit of a monster when it comes to many body systems. Right, so yes, we saw lots of talks on few-level systems. So if you apply this construction to just a two-level system, it was already pointed out in the early work by Demir-Plak and Rice that if you want to do rapid adiabatic passage, all what you need is a counter diabatic term that goes with, like a Pauli matrix Y. Yeah? Now, sometimes in the lab, it's not so easy to implement these Pauli metrics, and you would rather prefer to have it a control which only acts on the diagonal terms. And you can always try to find these controls by searching for a unitary such that you look for a unitarily equivalent Hamiltonian in which the new control now looks simpler. Yeah? So this kind of unitary just pumps some excitations into the time evolving state, but it will be equal to unity, the identity, at the end of the process. So actually, it still gives you a shortcut. So other simple quantum systems were considered. One is, of course, the driven oscillator. So you see then that if you follow the construction by Berry and Rice, what you get is kind of a squeezing term. And if you are thinking of ion traps or cold atoms, well, there's no way that you realize this kind of term in the laboratory. But that's not a problem because you can still play this game and find that the control can be absorbed in the frequency of the trap. Yeah? You can map it to just a harmonic oscillator term. And there were other works where also, like people look at transport, and if you want to cancel excitations during transport, then you will need a Hamiltonian which is linear in momentum, so almost like in relativistic quantum mechanics. But again, you can just look for a unitary and map it to a linear potential. So that's easy to do. Good. So there were a few experiments which demonstrated this counter adiabatic control in the lab. And one was applied to few level systems in quantum optical settings. So this was by my colleague, at least I know Sitzen well, who is one of the pioneers of shortcuts. And also Ki-Wan Kim, so he was able to implement this for fast transport in ions. Good, so this was, I guess, the general introduction of shortcuts. So in principle, there is a universal way of constructing them. You have to have access to the spectral properties of the system. This may be very difficult in many body systems, and I want to now move into this direction and see to what extent we can still control the dynamics of complex systems. And one is, arises naturally in the context of cold atoms, and is going to be essentially trap atomic clouds with different kinds of interactions. In particular, I'm going to focus on this kind of system where I have lots of particles of equal mass. They are all in the same trap, which is isotropic. It has a frequency omega t that we will drive in time. And particles can talk to each other through this pairwise interaction potential. And well, in cold atoms, there are, typically interactions are of contact type. And well, in some cases, this property is satisfied. So this is going to be very important for us because this is a system which is complex enough such that no one in the audience can find the eigenstates and eigenvalues, as you drive the frequency. If you take 100 bosons in 3 dimensions in a harmonic trap, it's not going to work. So, however, by imposing this symmetry in the interactions, it will turn out that we can simplify the dynamics a lot and actually just control it and map it to a very simple control problem. So the role of this constraint is essentially that the interaction potential is a homogeneous function of degree -2. So when you multiply the coordinates by a constant, you can pull out that constant with a power of -2. Is what you see in this little movie. You have a wave packet. This doesn't have to be a single particle wave packet. I just plot a Gaussian, but this could be anything. So you have a many particle system. You look at the density profile, so the density. And as you expand the trap here in blue, what you see is that the shape of the density profile is preserved during time evolution. So the evolution is self-similar, so it's scale invariant. Yeah? So all what happens during the dynamics is a scaling of the coordinates by some width, which is what is changing in time. There will be excitations in the phase, but this is, if you just look at the density, this is what you will see. And I emphasize, no, this has nothing to do with Gaussian variational ansatz. This doesn't have to be a single particle Gaussian. It could be a Tonks-Girardot gas or some other many-body system. So I want to report this progress in the lab. So there was an experiment done by Haibin Wu. He was a postdoc at NC State with John Thomas, and he's back to China, to where he has in Shanghai a very nice lab we had the chance to visit. So on the theory side, there was Aurelia Senu, Ivan Kulami, and myself, and we essentially, they essentially managed to implement shortcuts to adiabaticity in a system which is relatively complex, I would say. So let me describe it a bit. So the system is the following. It's similar to the one I presented before, but it's made of, it's a spin 1/2 Fermi gas, so maybe say 1 million particles, lithium atoms prepared in a balanced mixture, so in 2 hyperfine states. So effectively, you can think of having a spin 1/2 component. And they have some kinetic energy, they are trapped, but there are interactions between atoms which are in different hyperfine states. And again, this is a system which will be hard to describe. Actually, for general interaction, not even the eigenstates are known. Is under current, intensive studies, in particular when the interaction constant is large. So it turns out that in the laboratory, in cold atoms, this is something you cannot do always in nature, but you can play with a magnetic field and change the amplitude of the interaction. So you can either set this to 0 or actually make it really infinite. Yeah? So for all practical purpose, you can take this G to be divergent. And the way to do it is just tune with an external magnetic field at different values. And there are resonances, so-called first-back resonances. And this will allow you to essentially either kill this term, so that will be then an ideal spin 1/2 Fermi gas, or you can crank up the interactions and bring it to what is called the unitary regime, which is a paradigm of a strongly coupled quantum system where pretty much all mean field theories fail. Yeah? Right. However, in these 2 extreme cases that I single out here, one recovers this nice property that I mentioned before. So we know that the dynamics is going to have this self-similarity. So the density profile just will be scale up or scale down during expansions and compressions. So this is how it looks in the lab. Yeah? So it's, these are pictures I took with my cell phone. So this is the cloud of a unitary Fermi gas, which is fluorescing, and for imaging, it is, and you can record essentially pictures with a CCD camera, and you need exquisite control to be able to modify the trap in time in a prescribed way. So essentially how the trap is made is just by 2 orthogonal laser beams, and the power intensity of these lasers sets essentially what's the frequency of the harmonic trap, effectively harmonic trap, and it can be tuned independently along different axes to realize these shortcuts. So the experiment typically starts with a thermal cloud. There is a process of evaporative cooling. You reach a degenerate Fermi gas. You typically transfer the gas to a different trap, maybe use first-back resonances to prepare the ideal Fermi gas or the unitary Fermi gas, and then you can do a shortcut just by changing the power intensity of these 2 lasers. And finally, you probe the cloud with time-of-flight images, which is the typical way of probing ultra-cold atoms. So, we can go back to the picture we had before, and essentially we have this kind of model with spin 1/2, but it falls into this family. And the way of controlling the dynamics, even if you cannot really apply the construction by Demir-Clark, Rice, and Berry, because it's really impossible, it turns out that you can just exploit self-similar dynamics to come out with this extremely simple prescription, in which if you want to drive the system through a reference trajectory, which is parameterized by omega of t, so you change the trap slowly, and you say, this is how I want the cloud to evolve. Well, if you want to speed up that process, all what you have to do, instead of implementing this frequency, is to implement this other frequency, which depends on the reference trajectory, but as well on derivatives of it and kind of second derivatives. Yes? Very, very simple prescription to control the dynamics of a system which otherwise is is really complicated. So let me show how we probe whether we succeed is essentially by comparing the radius of the cloud. So the radius of the cloud, we engineer an expansion, and we expect that it grows from some initial value until some final value. And if we do not do a shortcut, if we just do a regular expansion, what happens is that the radius of the cloud grows And it's a non-equilibrium state, so it doesn't stay at the equilibrium value corresponding to the final frequency. It oscillates, and that means that you have excited the cloud. So the cloud expands, and instead of reaching an equilibrium state, it just breathes, so the cloud keeps changing in time. And you see that depending on whether you have an ideal gas or a unitary Fermi gas in orange, the oscillations have different frequency and different properties. So this is what happens if you excite the cloud. You just try to expand it, and you pump excitations, and you see them in the radius of the cloud as a function of time. Now, you can do shortcuts both in the ideal Fermi gas and the unitary Fermi gas, and this is really what happens. The radius of the cloud grows, reaches equilibrium, and pretty much just stays at that value. Yeah? So this demonstrates that just by tuning the frequency of the trap in the same time scale, so I'm really driving the system in a time scale where I can expect huge oscillations. By using a shortcut, I managed to reach equilibrium and essentially keep it at equilibrium with no excitations. There's another way of characterizing how non-adiabatic I am, and that's by looking at the mean energy. And for systems which have scale invariance, you can always relate the mean energy to initial properties of the system, either its initial mean energy, its initial squeezing, and initial particle fluctuations. Yeah? So this is an exact solution. If you have a scale invariance, this is always the case. So these operators form a closed Lie algebra, and then they determine the evolution of any of them, in particular the Hamiltonian, which gives you the mean energy. So what's this B? So B is essentially the radius of the cloud, or really the expansion factor of the radius of the cloud. And it just obeys this classical, simple second-order differential equation, which tells you how the radius changes when you change the frequency. Now, with that, we can essentially write a relation between the non-adiabatic mean energy and the adiabatic one. And we can identify this factor, which is going to tell us how far from equilibrium we are, how much excess of energy we have. If Q is equal to 1, we will be in the adiabatic limit. If Q is larger than 1, then we will have excitations. And it turns out that we will be able, essentially this factor is just related to the radius of the cloud, so we will be able to image it, yeah, to get it from the data. So the experiment, again, engineers an expansion. It's a control expansion, from some initial cloud to some final expanded cloud. And we want to demonstrate that this factor can be equal to 1 even when we go very fast. Equal to 1 in the final state, such that we don't have any residual excitations. And, well, this is the data. We compare a regular expansion where the cloud is driven and excitations start to build up, and they're in the final state. So this is a regular expansion where no use of shortcuts is made. The curve in red is actually a shortcut, and then you see that along the process there are energy excitations. So the cloud is excited, then it reaches 0, then it's excited again. But what is important is this final point, which tells you that at the end of the process, the energy matches the adiabatic value with no excitations. So again, this demonstrates, I guess, just by looking at the radius of the cloud and also estimating the mean energy, we can demonstrate that it is possible to create shortcuts in this kind of many-body systems, which otherwise would be kind of difficult to control. Yeah, so recently, just today in the archive, we reported some further progress. So what we did is so I have been cheating a bit so far to simplify the presentation. In the laboratory, the trap is not symmetric, it's anisotropic, and then there are different axes, and these axes are coupled. In principle, this is not a problem at low temperature, but if we heat up the cloud, then temperature plays an important role. So these are just some ugly equations. What happens is that the dynamics becomes viscous, so there's viscosity, and as a result, we will not be able to control the cloud. Yeah? So there's now the evolution of the radius of the cloud depends on some coefficients and some shear viscosity, and that limits essentially the ability to do shortcuts. Now, one nice property is that even if your trap is anisotropic, you engineer for an isotropic expansion, then viscosity plays no role. So it is possible to do shortcuts even at high temperature. And this is what you see in this plot. Now we have the cloud is anisotropic, so the radius along one axis is different from the radius along a different axis, but you see that we can do expansions in which essentially we have no excitations in either axis. So this is a high temperature. We know that there is viscosity, but essentially it plays no role because we engineer isotropic expansion. Yeah? So we focus on isotropic expansions. Now, if the expansion is anisotropic, then we cannot disregard viscosity. And while one of the axes has a nice expansion, the other one actually has a compression. So this transfer of the axes are coupled, and there are also residual excitations. So in this case, we just do not know how to control the system. Yeah? And this is mainly because we don't have anymore a superfluid. This is very heated up, and viscosity plays a role there. Okay, so this was essentially a part of the talk where I wanted to mention that it is possible to control the dynamics of complex systems even when we do not have access to the spectral properties. And in this case, it was a cold-atom setting, and we had to make use of the symmetries, dynamical symmetries of the problem. And this is what allows us to essentially engineer these shortcuts without any external controls, actually. Right, so in the next part of the talk, so this is essentially the last part, I want to move to spin systems, and in particular systems which spin systems which have a phase transition. So it's going to have, we are going to have a spontaneous symmetry breaking, and this will hinder the possibility of doing shortcuts in some sense. So we are all familiar with spontaneous symmetry breaking. So the idea is you have a spin system, maybe at high temperature is in a well-defined phase, and you cool it down in time, and then you know that there are different ground states where spins all align along a given direction. And if there are no magnetic fields, the different ground states are degenerate, and then the question is what happens when you drive a system in finite time through a phase transition and force the system to choose one of these ground states. So of course, what you get are domains. So this is where different parts of the system choose orientation of the spin along different directions, and the interface between different domains is what is called a topological defect. So when you have, the dynamics of a phase transition is in general quite complex, but there's a kind of a hand-waving theory which is very successful, is the so-called Kibble-Zurek mechanism, which tries to estimate what's the size of the domains and how many domains you get as a function of how fast you drive the system. Yeah? So there was Tom Kibble, who was at Imperial College, and Wojciech Zurek. So they engineer, they develop an argument to predict the average density, the average size of the domains and the density of excitations, the density of domain walls. So there are early works, it's relatively old. It was developed in the mid-70s and further later on. And for quantum systems, it was proven in 2005. So it also holds, and the idea is that if you drive a phase transition in some time scale, tau q, then the density of excitations is going to scale with the time in which you cross the phase transition as a universal power law. So it's a very simple prediction. It's universal, and it tells you that if you want to suppress defects, you have essentially to rely on very large quench times, so drive the system very slowly. So essentially, it's kind of a statement of how adiabaticity breaks down in a phase transition. So there's, to study phase transitions, there are several models, and you know that there are universality classes, and some models are paradigmatic, so they are very important and capture most properties. And one is the simple quantum Ising chain, where you have a one-dimensional chain of spins which talk to each other through nearest neighbor interactions, and there is a magnetic field. Now, by changing the magnetic field, you can access two phases. One is the paramagnetic phase, when this term wins. So if G is very large, then all the spins align along a given direction. If the magnetic field is very small, then the interaction term wins, and there are two phases, two different ground states, where spins are polarized, all parallel, either pointing up or pointing down. And now the question, of course, is what happens when you drive the system in finite time. So you go from this phase to this phase, and you expect lots of coherent excitations of this kind of kinks between spins up and spin downs. So it was shown by Jacek Jarmaga in 2005 that the average density of kinks, so these domain walls, these kind of excitations, in this system is given by this expression. So this is the number of spins times the density, gives you the average density of defects. And what is important is the scales as the Quent's time. So this is the time in which you go from this phase to this phase. So again, if you want to suppress excitations, you need to rely on long Quent's times, and then you just get one of these very weak power laws with a 1 over square root of time. So this is essentially, this is considered to be a confirmation of the Kibble-Zurek mechanism in the quantum domain. And it was observed just by digital quantum simulation. There were experiments which measured the number of kinks versus the Quent's time, and essentially found a power law behavior which essentially is consistent with the prediction in this paper. Yeah? Now I want to mention that it is possible to go beyond the Kibble-Zurek mechanism. So this is a work that I pretty much did here during this program, and I reported it last Friday. It appeared on the archive. One can also look at the full counting statistics of defects and get the full distribution. Yeah? So this is, I think, in the talk by Sylvain, they were able to already start to measure these kind of things. So this is the probability of having n kinks, so n topological defects. And you can just compute it either analytically or numerically, and so that this is, if you go fast, so you have this kind of distribution. So and then you can do slower quenches and slower quenches. And what you see is, of course, that the average value of kinks reduces. So this is kind of a adiabatic theorem, but also the dispersion, the variance is decreasing. And it looks pretty much like it's a Gaussian distribution. So the claim is that this may be universal. So the probability of having n kinks is just given, is peak at the value predicted by the Kibble-Zurek mechanism, but now the variance is also predicted by the Kibble-Zurek mechanism. So there's universal scaling both in the mean and the variance. Yeah? And D, again, is this estimate which was derived by Jarmaga. Right, so whenever you have a probability distribution, you can take its Fourier transform, and that will be the moment generating function. And if you take the characteristic function, so if you take the logarithm of the characteristic function, this is the so-called cumulant generating function, and it's known that it has a power series expansion, or this is the way to define cumulants in this way. Yeah? So it turns out it is possible to show that the cumulant generating function is essentially given by this expression, and this will be just you can expand this as a function of theta. Theta is the variable conjugated to the number of kinks, but what is important is that all cumulants, kappa of q, are proportional to the mean value of kinks. Yeah? So maybe it's better to just make a plot. So this is what I mean. Essentially, we can plot all the cumulants versus the time in which you cross the phase transition. And in a double logarithmic plot, so power laws should appear as straight lines. The first cumulant is just the density, and this is the one which is predicted by the Kibble-Zurek theory to scale as a power law of the Quent's time. But what you can show is that higher order cumulants, such as the variance of the number of kinks, or the third cumulant, which is just the third center moment of the kink number distribution, all scale as a power law with the Quent's time. Right, so I think this is an important step forward in understanding topological defect formation in phase transitions, because it goes beyond just characterizing the mean to also characterize fluctuations, and clearly higher order cumulants are non-zero, so that means the distribution is actually non-normal. Yeah? So there are correlations. Good. So this is what we know. So this essentially, if we when we drive a phase transition in finite time, there is no non-adiabatic dynamics that leads to the formation of kinks or topological defects, and there is always this kind of scaling which is universal with the quench time, and at least studies which has been done for the mean density of kinks show that this is very broadly applicable, and 40 years of research have shown that this kind of arguments apply to integrable models, non-integrable models, a wide variety of experimental settings where results have been found to be consistent with this universal scaling with the quench time. Again, it's kind of bad news if you want to suppress defects, because it tells you that the suppression of defects goes with a power law of the quench time, so you really need very long quench times to favor adiabatic dynamics. So one possibility is to do shortcuts in this context and try to avoid the formation of topological defects. Yeah? So one first idea, which we elaborated a few years ago, is just to implement the prescription by Rice and Berry and try to implement this counter-diabatic Hamiltonian across a phase transition. Yeah? It turns out that if you focus on the Ising chain, this is simple enough so that you can actually diagonalize the system. So your system Hamiltonian, you can find essentially the eigenstates, and you can also write down exactly what will be the control term that suppresses the formation of topological defects across a phase transition. Now, this is a beautiful expression which is very compact, but it's compact in Fourier space, and when we go to a spin space, this really involves high body interactions, like one body, two body, three body, four body, and so on. So it may actually be not realistic at all. Yeah? So this is, we were aware that in principle it is possible to suppress defects, formation of defects across a phase transition using this counter-diabatic driving scheme. The problem is that the interactions you need to implement in the laboratory to do so are completely crazy. Yes? So they are very complex. So what we propose, so this is a plot where we essentially compute the density of excitations, the density of topological defects, versus the velocity at which we cross the phase transition, so inverse of quench time. And if you do nothing, we know that we have this power law, which is predicted by the Kibble-Zurek mechanism. So this is this power law. Now, we want to suppress defects, and one thing we can do is, of course, is to try to add this term. And with this term, there will be no excitations whatsoever. The problem is that adding this term, again, requires high range interactions. So what we thought is maybe yes, we should truncate the interactions and consider only two body interactions. Or, so this is how efficiently you can suppress excitations with respect to the Kibble-Zurek theory by using one body interactions, two body interactions, three body interactions, four body, and so on. So well, eventually, if you go to high enough, 7 body interactions, then you see that the density of excitations is completely independent of the quench time, and then you have suppressed the Kibble-Zurek mechanism. There are no excitations, no topological defects formed, and essentially you have engineered a shortcut. But this is, but you still have to implement this kind of very exotic counter-diabatic interactions, and there are some techniques to do that, but this is really challenging. So before the experimentalists in the audience kill us, we decided to talk to people like Klaus Mollmer and Thomas Opatny, who had introduced a technique to try to simplify this. And the idea is, okay, you know what you have to do, so this is completely crazy, but maybe it still gives you inspiration of how to engineer more realistic control terms. And assume that in your laboratory, you only can implement maybe one body terms, or maybe two body interactions. So the prescription by Thomas and Klaus, which was put forward in this paper, is you can always try to approximate your counter diabatic Hamiltonian, or the control term, in terms of the available controls in your laboratory. And all what you have to do is to determine which are the coefficients which optimize the suppression. Yes? So you can minimize the norm difference between the exact control and the one you think you can realize in your lab. And essentially, this will give you a prescription. So this is something we put forward in this paper, which I thought I should mention given the audience here. And what we saw is, you can plot now the infidelity as a function of time. And what you see is, well, if you do nothing, then essentially you have lots of excitations. But it is possible to, just with two-body interactions, to gain a few orders of magnitude, nearly 2. And if you have access to three-body interactions, you already gain like 7 orders of magnitude. So we don't really have to engineer 7-body or 50-body interactions, which is what the theory tells you. But you see here that you can approximate efficiently your counter diabatic controls with simple two-body terms. Still, maybe I should mention that they can be non-local, so it still can be tricky. Good. So if you just use counter diabatic driving in a phase transition, you get something very challenging to implement. If you use the ideas of Thomas and Klaus, you can improve upon that and essentially maybe find an efficient approximation of the controls to suppress defects. And okay, you can gain some huge amount actually of orders of magnitude, but these interactions may be still non-local, so still difficult to implement. So then what we thought is, well, what if we forget about really using auxiliary control terms and drive a system locally? So we will never change the system Hamiltonian. We will just change the parameters of the system in a different way. And so this builds on some ideas I discussed with Tom Kibble and Kibble-Zurek in this couple of works. This is actually a review, but it includes all the ideas we developed there. And the idea is, if you are going to cross a phase transition, don't drive the whole system at once. Just do it locally. So you start driving a system on one side, and then you eventually sweep the critical point throughout the whole system. So the hope is that if you first break symmetry in one part of the system, this breaking of symmetry can bias the breaking of symmetry in neighboring regions, and in such a way a single domain will grow and you reduce the number of defects. One of the ways, so this is kind of the setting we have. Now we have an ion chain, which is, a spin chain, which could be an ion chain, which is inhomogeneous, and then the interactions between the spins are position dependent. Yeah? And in this case, we can drive the chain with a constant magnetic field, constant in space, is changing as a function of time. And as we vary the magnetic field, then the phase transition will start in the center of the chain. And then as you keep sweeping the magnetic field, other parts of the chain reach criticality, and eventually the whole chain reach criticality. But the point is, the phase transition starts first in a part of the system, and then eventually goes throughout the whole system. So this is the idea of going from homogeneous driving of the system to inhomogeneous driving. And the important prediction that we have is that the density of defects, which in this case is predicted by the Kibble-Zurek theory, under inhomogeneous driving exhibits still a power law with the quench time, but now the power law exponent is much bigger, and this allows you to suppress defects much more efficiently. And here we do not need any auxiliary control terms. So this is, the resolution actually is not very good, but here you see the density of defects versus the quench time, and we compare what happens when you drive the system globally, and then, so this is the Kibble-Zurek prediction, and then defects, this is adiabatic dynamics, and here fast quenches, you have saturation of defects. But if we drive the system locally, you see, which requires no 7-body interaction or anything like this, it's just local driving, changing the magnetic field in space and time. Then what you see is that you always reduce the density of excitations by a few orders of magnitude with respect to the global strategy. Yeah? So this was actually the early ideas were put forward in these papers. This was essentially motivated by classical problems. And this is actually the first demonstration of this in the quantum domain of this inhomogeneous universal scaling of the density of defects, which is always smaller than that under global driving. Right. So with this, I'm closing. Actually, maybe it's a bit early, but essentially, I want to mention that there's a general way of controlling systems using this counter adiabatic technique, which requires access to the spectral properties of the system. But we have shown that in quantum fluids, we can avoid that by just using dynamical symmetries, such as self-similar dynamics. And in the context of phase transitions, we have shown as well, we have developed a theory that goes beyond the Kibble-Zurek mechanism to characterize the statistics of topological defects. And then we have also shown how this can be suppressed. Yes? So I just want to thank my collaborators, in particular, my group at UMass, and theory collaborators for the first part is Aurelia Senu and the group of Haibin Bu at East China Normal University, and Ki-Won Kim and so on. So with this, I just want to thank you all for your attention. Yeah.
I have a number of questions. So the first is on these shortcuts to adiabaticity. So if I think of them from a control point of view, I can think of them as being like an end point task, right? Because you are putting the objective at a final time, just making sure that.
Yes, yes.
Do you think that there is a way to define a similar problem, but maybe putting like a stroboscopic tracking, or like requiring that the solution is the same as it would be, but not just at the end point?
Well, I mean, sorry, but this essentially enforces the adiabatic following at all times, yes? Not
that
just at the end point. That is what I got
confused, because in one way you said it end
okay,
point, but then
right.
it was trajectory.
So you see, so if you implement this original recipe at every single time, from the beginning to the end of the experiment, the trajectory is the adiabatic trajectory. Yeah. So of course, you have changed the Hamiltonian, so that adiabatic reference trajectory is non-adiabatic with respect to the driving Hamiltonian.
Right.
It has to be. But what we have seen is that typically this term may be difficult to implement in the lab. So when we make use of these unitary transformations is when along the trajectory we leave the adiabatic manifold. We pump excitations, and maybe we can still choose this unitary to be the identity at the end of the process, and then we go back. So this was the pictures for the quantum friction that essentially show that you leave. Right. You pump excitations. And then, but then you are back. So here, there is no way we do the exact counter-diabatic term for a unitary Fermi gas. This will be kind of a spin-squeezing term for matter waves.
Let me ask the question again. Can I imagine that you have a protocol which does this trick, but not just at one time? Maybe if I choose to have it happening at more than one time? Sure.
Yes, you can. Yeah. I mean, here you see it accidentally. For instance, we have we recover adiabatic dynamics at some given point along the process, yes?
No, but I want to recover it in a predetermined way.
Yes, it can be done, yes. In this case, we actually know where excitations are coming from, so we can impose adiabaticity at an arbitrary number of points. What happens is that the amplitude of the controls is going to increase with the quench time. So for instance, so the idea is, imagine this is a good point, but this is shorter than the running time. So the amplitude of how you have to change the frequency of the trap scales down as 1 over the time in which you run the process.
Okay, maybe I will ask you later. My other question is on the phase transition and the Kibble-Zurek mechanism. You have never mentioned, and I was curious to know how these approaches compare with the use of optimal control approaches for minimizing the defect production in the same model. Various people have done it.
That's right. Yeah, for instance, I remember a work by
Polkovnikov, Sarofazio, lots of them.
Yeah, so shortcuts to adiabaticity don't beat, well, wait a second, but there are, I mean, it's hard to pose the problem, yeah? So what are they changing, yes?
Parameters in the in the system Hamiltonian.
Right.
But the objective is the same.
It's a hard comparison.
Why?
Well, because here we are changing the Hamiltonian. So we can always go arbitrarily faster and we can beat anything at the cost of creating these very difficult interactions, yes? So we can speed up a process arbitrarily, to run it in arbitrarily short times. Of course, the difficulty is we have to be able to implement the controls. And the controls in this case involve non-local interactions, yes? So the right comparison will be what is it that I can do with shortcuts just by changing the same parameters of the Hamiltonian, yes? But this is not a comparison I can do with counter-diabatic driving. Counter-diabatic driving demands you to introduce other controls.
Do it with the inhomogeneous driving.
Well, so in homogeneous driving, so it has not been compared with optimal control, as far as I know. But it's now having a huge impact in the context of quantum annealing, so people are rediscovering it, and there's many works on how this can give you a strategy for quantum error suppression in quantum annealing. Yeah? So, but again, there's no comparison that I know of with respect to time optimal control.
Anybody? Otherwise, I continue. So,
you have to take it offline. Okay, so I'm sorry we're out of time. So let's thank the speaker and